from GEM Elettronica, who will introduce the principles of inertial navigation system and discuss the impact of photonic integration. So, Leonardo, the floor is yours. Thank you.
Thank you, Christina. This is the first webinar. It's the first of a series of webinars that will treat this information about Photonics Compact Sensors, Inertial Navigation System, and also aidings of Inertial Navigation Systems. The floor will be shared by me, Leonardo Daga, from GEM Elettronica and the director of the Plants Lab. Then Matteo will follow me from Sigma Ingegneria. He will present himself after my presentation, and then Deep will from Endurosat will follow Matteo. I will speak about inertial navigation systems. In particular, I will keep some topics like the purpose of inertial system, the type of inertial system and algorithms, the inertial sensors and their characteristics, and the new technologies from INPHOMIR project. Then Matteo and Deep will talk about applications on drones and the nanosatellites. About inertial navigation systems, first of all, I want to introduce GEM Elettronica. GEM Elettronica is a company in San Benedetto del Tronto, Marche, and is a manufacturer of radar systems since 1977, and the manufacturer of inertial systems since late 1990. I'm the director of the Plants Lab, that is a research and development group for navigation system and quantum application. We'll manufacture a lot of systems for ship, for ground system, for underwater, for many applications, and civil and military ones. The overview of my presentation will be the purpose of inertial systems, the inertial sensors and aiding technologies, how different needs drive the selection of proper technologies, and the emerging technologies that are introduced by INPHOMIR project. Some words about the purpose of inertial systems. First of all, the inertial systems are made to provide attitude stabilization. In this case, the primary information used is the measure itself, and is used to stabilize the attitude of a platform, but using not the measure of the attitude, but the motion of the attitude, the motion of the platform. This is essential for stabilizing cameras, antennas, and other systems on moving platform. The next step is to provide platform orientation, system that provide platform orientation, that means attitude determination. In this case, the system needs to estimate roll, pitch, and yaw using gyroscopes and accelerometers, like in the previous application. This is critical for applications like autonomous vehicles, aerospace, and robotics. The step ahead is the providing the continuity of navigation and overcoming limitations of a satellite navigation system. It means that it's inertial navigation system that allow to operate independently of external signal, providing continuity in positioning, because the positioning aiding like GNSS can be obstructed or jammed, or maybe are not available because of the environment, like in underwater applications. Why inertial systems are important today? Because there is an expanding demand of autonomous navigation. There is a need for positioning and for control of autonomous vehicles, drones, and robots. And there is a need for faster and smarter mobility, in the sense that there is need for reduced delay, optimized routes, for transportation of people and goods that relies on precise and uninterrupted navigation, and to provide machines with human-like spatial awareness, because this environment is mainly made for humans, and machines need to move in this environment. So they need to be precisely positioned and to be autonomous in this environment. Inertial sensors are mainly the accelerometers and gyroscopes. The accelerometers are used to measure linear accelerations. It can be made by two different kinds of technologies: the MEMS technologies, the technology that is compact, low cost, and suitable for consumer and automotive use, or the quartz accelerometers that have higher accuracy and is used in professional and industrial applications. The gyroscopes are made to measure angular velocity. In this case, also the technology that can be used is the MEMS technology, that is small and economical, but with higher drift in the measure, or the optical or optomechanical based technologies like fog, or the RLG or HRG, that are technologies that allow to have a much better measure of the rotation rates, and comparing to the MEMS sensors, but this more accuracy comes with some cost in size and the power consumption. Obviously, you need to tailor your system and sensors that you choose, selecting the proper sensors respect to the specification of your application. So you need to find a trade-off between power consumption, cost, and accuracy. Inertial sensors are characterized by a drift in their measure, the integration of their measure. So you need to have also external information provided by aidings, named aidings, like speed sensors, LiDAR, optical flow sensor, vision-based system, magnetometers, barometers, or altimeters, that are, I define this like internally referenced aiding sensor. It means that they don't need an external structure to provide this measure. Otherwise, there are also externally referenced aiding sensor, like a positioning sensor like GNSS, like GPS, or the European constellation or Chinese constellation, to provide absolute position and velocity, but this is vulnerable to jamming, or the marine positioning system, like USBL, LBL for underwater navigation. As I said, aiding sensors are necessary because the INS systems without aiding may accumulate drift in the positioning and in the attitude. So talking about, as I talked before, there are three application levels: the attitude stabilization, the attitude determination, or the inertial navigation. These different cases require different solution, different algorithms, complexity, and implementation cost to be implemented. And choosing the right configuration of sensors and algorithms provides you the best performance and best selection for the environment and budget, the considered environment and the budget you need to have. And the sensor fusion between internal sensors, inertial sensors, and aiding provides is the key enable to get the maximum accuracy for your application. first of all, the first step is the attitude stabilization. As I said, in this case, you don't need to elaborate much the information that you get from inertial sensors. In this case, what you need is continuous and control and the counteraction of movements. In this case, you just need the raw measures from the sensors, so acceleration and rotation rates, and to get a real-time correction. That is what is essential. And in this case, you don't need a full set of sensors. You may need even a couple of gyroscopes, or maybe a couple of accelerometers, or a combination of this. Not 3 accelerometers and 3 gyroscopes that are a full set of sensors. And the algorithms that may be applied here are maybe very simple, like a PID controller or a complementary filter to blend fast and slow signals. The sensors are used, as I said, gyroscopes and accelerometers. Typically, you don't need very accurate sensor, but it depends on the application you are creating. The next step is the attitude determination. In respect to previous step, you need to know exactly which is your roll pitch, and in case also heading. So the full orientation in 3D space, or just roll and pitch, because this is something that is essential for autonomous vehicle aerial system, and maybe just and some platforms. To be georeferenced, and if you need just the orientation respect the vertical axis, like a roll and pitch, the main information comes from the accelerometers that compare their measure to the gravity vector. In this way, you get the information of roll and pitch, just comparing these two vectors. And the gyroscope is to reduce the noise and transient error, because the acceleration that you measure with the accelerometers is not only composed by the gravity, but is composed also from by the apparent accelerations. Here, the algorithm that you can use to get the measure of the attitude are quite easy, like Kalman filter or gradient descent filters, and you can also fuse multiple sensors, not only inertial sensors, for example, to determine the latitude in which you are computing this information to get more accuracy. But if you need to have also heading, then you need to have more information. So you need a full set of sensors. And maybe if it's okay for you to get only a magnetic heading, because it's okay to have the orientation respected to magnetic north. So it could be as external heading, external aiding. You can use the magnetic magnetometer that measure the direction of the magnetic field locally, and compares to the one that you expect in that place. And so you can get the magnetic north. But this north is different from the geographic north. I mean, depending on the place where you are on the Earth, but it could be different even by more degrees. Many degrees, so you can also use GNSS differential heading, and it is obtained using a couple of GNSS antennas, for example, and you compare the time of arrival of the signals from the GPS GNSS to the antennas to determine the orientation of GNSS antenna respect to each satellite. And composing the information, you can get the GNSS heading. But this information is quite delicate, it's not so reliable, because it's quite noisy and can be easily jammed. So if you need to have very reliable heading, you need to have a higher grade gyroscope, because in this case, using a high grade gyroscope, you can measure, you can estimate the direction of the rotating axis of the Earth. But given that it's very weak signal, the rotation of the Earth, that is 15 degrees per hour, sorry, then you need to have a very accurate sensor, because, for example, MEMS sensors typically cannot measure below 1 degree per minute. They are not very accurate up to degrees per hour, sorry. And so this is the, you need like optical gyroscopes or similar. The next step is the third step, and the more complex step is to, if you need to have an inertial navigation system, in this case, you need the full information, so position, velocity, and attitude in 3D space. And in this case, and this typical for autonomous vehicles, submarines, aerospace systems, or navigation in GNSS-denied environments. The algorithms used in this application are based on Kalman filter or more advanced filters, but these algorithms require, typically the Kalman filter require an accurate modeling of the kinematics of the rotating Earth, together with all the kinematics that point on the spherical surface needs. And to model the sensor errors like biases and scale factors, and also model the external aiding sources and their errors. The sensor used in this case, depending on the application you need to create, are, for example, if you need a standalone operation a system that can operate in a sustained standalone operation, then you need a high-grade sensors, because they allow you to have a great autonomy respect to a GNSS denied scenario. While if you don't need so much autonomy from external aidings, then you can use also low-grade sensors like MEMS-based sensors, but in this case you rely heavily on frequent aiding to limit the drift of positioning. In this case, this last case, with low quality IMUs, the INS practically interpolate between aiding updates rather than truly navigating itself. A few words about the relevant characteristics of inertial sensor to select the good inertial sensor for your application. Obviously, you need to select the range of measure of the inertial sensors. While the long-term offset is something that is typically calibrated, but you need to check also the session offset, typical session offset of these sensors, the bias instability of the sensor, the measurement noise, and also the scale factor error. That is a second level error. A proper understanding of these errors is fundamental, because the navigation algorithms are tailored on these errors, and they can compensate part of them, but they need to know, and you need to know which is the entity of these errors. For example, here I show the typical noisy measure from the inertial sensor. For example, here the green dotted line is the real value to measure from the inertial sensors. In this case, is the rotation rate. Typically, you get from the sensor a noisy measure. This is the blue line. The blue line, as you can see, but is typical, has a bias respect to the real value to measure, and this bias is what I call it run-to-run bias is typically a difference with respect to the real value to measure that is changing session run-to-run. Each session has a different value. And this typically something that you can estimate during the session using information from the aiding sensors or the model that is inside the Kalman filter. But you typically need to have aiding to estimate this run-to-run bias. Apart from this, there is an oscillation on the respect to the run-to-run bias that is named bias instability. This bias instability is something, both the run-to-run bias and the bias instabilities are both characterized in the specification sheet of the sensors. And you know which is the entity of this bias instability, that is a fluctuation respect to the average value of the session. And you need to know this bias instability because it's something that is typically not removable from the measure unless you have a very frequent aiding, but it's typically something that remains and very important. You cannot remove it when you have no aiding at all. So the bias instability is something that characterize a lot and condition a lot the navigation, inertial navigation, when the aiding are not anymore available. Then there is the white noise. The white noise that is superimposed on the bias instability. That is a noise with the zero average and the standard noise that I mean is not a problem by itself, but on the measure, but it's a problem when you need to integrate the measure from the sensor, because for example we have accelerometers and gyroscopes that measure respectively the acceleration and the rotation rate, and you need to integrate this measure to get, for example, the position, the velocity from the acceleration, or double integrating, you get the position, or the angles from the angular rates. When you integrate the white noise, you get an effect that is called a random walk, that is a drift on the position or on the velocity or on the angles that is depending of the entity of the white noise, or the sigma of the white noise. And this drift increase with the time, with the square root of the time. And you need to take care of this information, because integrating inertial sensor, you will have this drift on the result that you cannot remove unless you have some aiding. There are not only external aiding, there are also mathematical aiding. The first of all is the one that I already described. You have the gravity that helps you to have always a reference that help you to compensate the gyroscopes, because you know always where is the down direction. And you in the long time you can compensate the drift of the gyroscopes. But there is also the Schuler effect, that is a mathematical internal, I would say. If you create a very good model, a good model of the earth kinematics, you have this effect, the Schuler effect. That is, I don't want to enter too much into detail of this, because it's quite complicated to describe, but you have that moving on a spheric surface, there is a connection between the rotation and the velocity. And if using this connection, you can feedback the velocity with the angular rates. So the model that is inside the Kalman filter knows when you are moving, because you are also rotating. And if there is no rotation, then the model inside the Kalman filter provide a feedback that help the solution not to drift indefinitely. But to use this effect, given that the movement of on the Earth is corresponds a very weak rotation. For example, here there is an example. Velocity of 1 nautical mile per hour corresponds to 0.0168 degrees per hour. So it means that you need to have a very accurate gyroscope. Typically, MEMS can measure up to degrees per minute, maybe 10 or even 1 degrees per hour, but this value is not reachable at all by MEMS. And you need to have very accurate gyroscopes to compensate and to exploit this effect. Just a few words about the technology that GEM Elettronica is typically using in our inertial systems. It is the fiber optic gyroscope technology. Fiber optic technology is based on light and on fiber. We generate using a laser a light that goes into a coupler, sorry, and then in a phase is split inside a phase modulator and enters inside a fiber coil in a clockwise and counterclockwise direction. This light comes back to the phase modulator and the joint of the phase modulator where it creates interferometry between the lights in the two directions, and that if the fiber coil is not moving, so the interaction, the interferometry is completely constructive. So the full light that enters inside comes back to the coupler and then to the photodiode, and then is converted using an analog to digital converter and then read by the control. But if the fiber coil is moving, is rotating, then the light that propagates clockwise, and if the system is moving also clockwise, arrives before the light that moves counterclockwise. And so that it creates a difference in the phase of the light that arrives to this point of the phase modulator, and then it may create a partially destructive interferometry. That means that light that goes to the coupler and then to photodiode is weaker, is lower, and this lower light is read by the converter and then by the control, and then you can drive a digital to analog converter to provide a voltage to the phase modulator to generate a phase to compensate the phase of the light here, and to get a full interferometry again, to compensate the light that is generated by the motion. And the voltage and the number that you provided to the converter and the voltage that you sent to the phase modulator is proportional to the rotation rate. So you have the measure of the rotation rate using this scheme. All these components are discrete components, are placed in, occupy some space. Also photodiode, the coupler, the fiber coil, and the more accurate you want to measure, the greater should be the fiber coil, and more space is required for this. And temperature affect all these components, and all this fog optical circuit is made by human operators. So human operators can, the production is not completely repeatable. have some difference between production to production. And so what we are doing in the INPHOMIR project is trying to put this scheme, like the fog, the interferometry scheme, in an integrated optical gyroscope. All the scheme is put in a single chip, photonic chip, with a light source, the few couplers. I mean, the scheme is slightly different, with still modulators, but the whole optical components are all inside the photonic chip, together with also the ring resonator, where the light travels millions of times to provide the same accuracy that is provided by a coil, or I mean, at least to be better than a MEMS sensor. And so all the optical components are inside the photonic chip, with some converter that and the control that is outside. But this means that the circuit is very, very reliable, and completely made by machines, and completely repeatable. And being the photonic chip, something great like that is 1 centimeter and something more as side, it's easy to temperature compensate this chip, and to have something that, from the environmental point of view, is very stable. The same, we are trying in the INPHOMIR project to create the same, use the same approach also to create a navigation aiding sensor. It's a LiDAR that is based on, maybe you know, and pulse generated by a laser that is travels to an obstacle and travels back, and from the delay from the emitted light pulse to the reflected light pulse, you get the distance. And using this distance, it could be used as a positioning, or at least to positioning aiding, or at least to minimize the drift on the positioning. A different application that we are also exploring is to use the frequency modulated laser to have not only the information about the position, the delay, but also the shift in frequency that can provide the velocity, the relative velocity respect to an obstacle. And this is technology that we are trying to implement in our INPHOMIR project. A few words about the project. The project is an European funded project, is a Horizon Research and Innovation Action. And we have German Electronic is the project leader. There are university partner, Polytechnic di Bari, the Technical University of Munchen, Eindhoven University of Technology, and University of Cork, and as end user Endurosat and Sigma Engineering that will follow me in this webinar. And One Hub as for the communication, dissemination, and exploitation partner. Here are my colleagues, Lorenzo Mancini, that is the project leader of the INPHOMIR project, Daniele Palaferri, that is a main investigator of the project, and Chiara Vecchi, that is also collaborating to this project, and me, that I'm just I would say the leader of the R&D group that drive this INPHOMIR project for General Electronica. So I leave the ground to Matteo for the presentation of the application made on drones.
Yes, thank you, Leonardo, for the excellent review. Now we move to Matteo Pacini.
Stop my sharing. Okay.
at Sigma Ingegneria, who will present real-world use cases and challenges in applying these technologies to drone and autonomous platforms. Matteo, please, you can go ahead.
Good afternoon, everybody. Thank you, Cristina, and thank you, Leonardo, for your presentation. I'm Matteo Pascini from Sigma Ingegneria, one of the industrial partner of the INPHOMIR project. Just a brief overview of Sigma Ingegneria to start my presentation. Sigma Ingegneria is a company founded in 2004 and has its headquarters in Lucca, in Tuscany, Italy. More than 30 employees and a lot of patents, so we do a lot of research and development, and we are glad to participate also in INPHOMIR project. And we do a lot of things, let me say, from design of automation, robotics machines to analysis, taking also a look to machinery safety, and we also have a production site for small and medium series. So this is the overview of my presentation. The first part is an introduction to our drones that will be the focus of our devices for the project, for the INPHOMIR project, starting from our brand for robotics and introducing our platforms. Then I will talk about the limitations of the current sensor technologies that we currently use in our platforms because of the availability in the market. And then I will talk about the performance targets of the new sensors that will be developed in INPHOMIR project. And finally, just some few words on application area for drones, considering our expertise and customers and so on. So, as I stated before, Sigma Ingegneria is one of the industrial partners of the INPHOMIR project, is an end user of the technologies developed in the project. So the sensor that Leonardo introduced before will be used in our drones, and then Endurosat will talk about nanosatellite. But talking about drones, I introduce our brand that is Drawings, because Sigma Ingegneria is a whole drone manufacturer. So we design, and build all the drones, starting also from the electronics and from the mechanical point of view. So consider that this opportunity to improve the performances of the navigation of the drone is a great technical and so also commercial from the all technical and commercial point of view. The overview of our platform, we start from our squad, that is the bigger one, is a quadcopter that can carry up to 8 kilograms payload, and that can fly up to 80 minutes without payload, and 35 minutes with the maximum weight. His build is completely designed by Sigma Ingegneria and built with lightweight materials such as aluminum, carbon fiber, also a lot of top parts 3D printed. It has custom, as I said before, custom electronics for power distribution, for remote ID, and also for is coming soon the flight termination system that is required from the European Aviation Agency. So this drone is a ready-to-fly drone with the carrying case that has an European Commission certification that is mandatory for these devices, and also the C6 marking according to European Aviation and Space Agency. So going further, the Helix project, it is the other let me say, the other two platforms that Sigma Ingegneria propose also for the integration in the INPHOMIR projects. are fully developed and built with innovative techniques. So our generative design, that is a new technique based on AI to obtain particular shapes that can be only 3D printed. So in the photograph you can see the two versions, the smaller one that is Helix 0 and the bigger one that is Helix 1. We have an active design patent on these drones, and that is a point of strength for the commercial point of view. Going further, just a brief overview to let you know what is generative design and the shape of this drone. Generative design, as I told you before, is an iterative design process that use AI to generate several shapes that satisfy a set of constraints, where the constraints are mechanical and geometrical. So the position of some components, forces, torques, and so on. This is a drone that has been developed in collaboration with Autodesk and is built with 3D printing. So the frame is a monocoque unique part, and it has optimized flight performances. So it has neutral dynamics that, due to only to its shape, that can is a characteristic that can assist the electronics to increase maneuverability. This characteristic is the bridge to the following part that is more related to electronics, that is the focus of this of the INPHOMIR project. So first of all, the first step that the Sigma Ingegneria decided to take is to use commercial command and control electronics. So open source PICSOC project with 6 degrees of freedom MEMS sensors with the redundancy. So there are 3 IM sensor with separate buses and separate power for, as I said, redundancy, vibration isolation, and temperature control. So this is the starting point. Some of our platforms can be equipped with this flight electronics, but we are developing and we will be ready in maybe 1 or 2 months with custom electronics that is important to reach some goals. So first of all, to break free from obsolescence and to have an electronics made in Europe. That is also one of the aim of INPHOMIR project. Low cost, high performance, and made in Europe sensors. This electronics is designed to integrate different types of sensors, so also the ones that we developed within the INPHOMIR project. As I stated before, we are in the engineering phase, so it will available for the INPHOMIR sensor integration. Let's talk about the limitation of the current sensor technologies. I talked about MEMS gyroscopes or accelerometers. There are a lot of challenges in terms of several characteristics. So drift that can compromise measurement accuracy, temperature sensitivity, because these environmental characteristics can impact on performance and cause other drift. Consider that the drone can be used in several seasons and can be overheated. So these things can cause drift. Vibration and mechanical noise, consider in this case the propellers, the manoeuvres, and so the noise in the reading of the sensor. Saturation, and so less accuracy in case of rapid and extreme maneuvers. Harsh environments, if the drone is used in survey, in environment that are dusty or so on, or are the landings, a collision can cause damages also in the sensor. So another challenge in using the current sensors. And also the moving part of the MEMS gyroscopes can be subjected to mechanical wear and tear over the time, so degradation. And then finally, the cross-axis sensitivity, where there is an influence between the motion along the axis. Then why introducing photonic sensors in the drones is a challenge for commercial and professional drones. So we are talking about drones that are used for mainly for civil applications, are for industrial and professional use, not for the main public. So the main purpose of using this sensor is a great precision and accuracy, and reduce the susceptibility to drift, because the sensor is more stable, resistance to external disturbance, for example, to temperature. There is also an increased durability and reliability also in a harsh environment with noise reduction. The angular velocity resolution is superior, considering the requirements in where the accurate motion sensing is very important. Efficient power consumption, that is one of the aim of the INPHOMIR project. And then these characteristics can also be related to simpler certification process, because the certification, as I stated before, is mandatory, so is easier to ensure compliance with the regulatory standards for electromagnetic compatibility, safety and environmental impact. Let's see finally which are the application, for example, that Sigma Ingegneria proposed to its customer, and that are the target also for the performances of the drone and also for the sensor. So in the photograph, you can see the Oro Squad drone that has been designed by Sigma Ingegneria with the payload of Caen, that is an Italian company that build radiological sensors. This drone is used for outdoor radiological search and monitoring purposes. So the main aim is to ensure environmental radiation protection and to do inspection in several sites, for example, after the dispersion of radiological and nuclear material. So one of the first, the target is the first responders for the exploration of hazardous areas, such as industries and so on. So this drone is equipped with the custom electronics that I described before, and that's height stabilization and navigation accuracy that are required for a precise source identification, so for a precise, very precise flight. Finally, another focal point of the project and for all the tasks that the Sigma Ingegneria is performing in INPHOMIR project is to developing software for autonomous navigation. So we are talking about obstacle detection and collision avoidance, real-time mapping and precise localization, and object detection and tracking through AI algorithms, adaptive navigation, and reinforcement learning navigation. In all these software modules, that I list, the sensors are very important because we are talking about avoiding obstacles to ensure safety flights and to improve the performances of the drone. So the sensor, the performance of the sensor is highly important. Here, finally, the contact, me, Matteo Pascini, project manager for the INPHOMIR project in Sigma Ingegneria, Simone Giusti, that is the CEO of the company, and Giacomo Pinagli, pilot and drone developer in Sigma Ingegneria. Thank you for your attention.
Thank you, Matteo, for your insightful contribution. Our final presentation today comes from Deep from Endurosat, who will explore the relevance of photonic sensors for satellite navigation systems and space applications. So Deep, the stage is yours.
Yeah, thank you very much, Christina, and thanks to Leonardo and Matteo for the nice presentation. Let me share my screen. Can you see?
Yes.
Okay. Hi, so my name is Deep Rajadari. I'm a senior GNC engineer at Endurosat and also a formation flight researcher at Technical University of Berlin. My purpose today will be to talk about the limitations with the current sensors on nanosatellites and how the outcome of the INPHOMIR project can contribute to the further development of nanosatellite missions. Before I proceed, I'd like to talk a few words about Endurosat. So the company Endurosat was founded in 2015. It's headquartered in Sofia in Bulgaria. Currently, we have about 230 employees, and we have offices across 6 countries around the world. Our newest office in Berlin was just recently opened last month. And Endurosat covers full mission lifecycle of satellite development. It specializes in manufacturing of satellite platforms, different sizes, and it also provides space services, different kinds of space services, from initial concept and design to mission operations. And it also provides testbeds for various kinds of payloads. And you can find more details about Endurosat at endurosat.com. So I will start with what are nanosatellites and what are its applications. So first of all, nanosatellites are just a subclass of small satellites, which are defined as satellites below 120 kilograms. This is not a hard definition because the definitions vary across literature. And then small satellites can be divided into microsatellites, nanosatellites, and picosatellites. And they are useful for variety of applications, for example, Earth observation, communication, navigation, and even for mission flying. And then the further step would be for rendezvous and docking, where 2 satellites actually collide in a controlled way and dock with each other. So today I will talk about the current angular rate, or the limitations of the current angular rate sensors, and how the integrated optical gyroscope can be used for attitude determination, and as well as how the frequency modulated continuous wave LiDAR can be used for small satellite proximity operations, which is when 2 satellites are flying very close to each other, or also trying to dock with each other. Yeah. So nanosatellites are smaller in size than the typical bigger satellites. They have constraints in finance, mass, volume, and also operational constraints. For example, in CubeSats, they are a type of nanosatellites, and they are expected to follow the typical CubeSat standards in mass and volume. And also because the manufacturers of nanosatellites usually have financial constraints, therefore they cannot decide their own launch date or orbits, because those are dictated by the larger commercial or government satellites, which are also flying on the same rocket. So if a nanosatellite needs to be deployed at 500 kilometers altitude, the final altitude can be anywhere between, let's say, 550 kilometers or even 450 kilometers. And this also comes with limited ground station contacts, which means that the number of ground stations allocated to contact with these satellites are limited, which means less data down on a particular day and less debugging opportunities in case something goes wrong. They have limited lifetime, so because they are built with economical components, a nanosatellite can be expected to work perfectly 1 year, 1.5 years, 2 years, but then slowly components start failing, and the lifetime can be extended partially to the next 3-4 years. But yeah, it depends on a mission to mission basis. And as I said, many components are not built for this harsh space environment. For example, many angular rate sensors which are used are MEMS sensors, and they are typically built for automotive industry. They are not built for space industry, which has its own a lot of disadvantages. And as I said, many electrical components, they start failing after a couple of years due to radiation or other reasons. But on the bright side, nanosatellites are an excellent test bed for demonstrating new technologies in space at a fraction of cost of the larger commercial or government satellites, especially for Earth observation or proximity operations in the low Earth orbit. And by low Earth orbit, I mean the altitude, which is, let's say, from 400 kilometers to 700 kilometers above the surface of the Earth. Okay, so what are angular rate sensors used for in orbit? So they are used for improving the orientation, like the attitude estimation in the sun phase. By sun phase, I mean the part of the orbit where the satellite can see the sun, or let's say where the sun sensors on the satellite can see the sun. And typically for determining its own attitude or the orientation, the satellite uses sun sensors and magnetic field sensors. The angular rate gyros are used to just improve that initial attitude determination, yeah, by using a Kalman filter, for example. The main benefit of angular rate sensors come in the eclipse phase, which is the point of the orbit where the satellite cannot see the sun. Yeah, so if you can see this here, so this part here, it's about 35% of the orbit at 550 kilometers altitude. And in this region, inertial navigation takes place. So the angular rate gyros, they propagate the last known attitude, and this must go on for the next 35 to 40 minutes, depending on the actual height of the orbit. And over time, the error in the attitude propagation, it increases. And an important note here is that I'm talking about satellites which do not have star trackers, because with star tracker, it can calculate the attitude at any location of the orbit. But on nanosatellites, because of mass and volume and financial constraints, star trackers are usually not flown. Benefits of rate gyros, MEMS rate gyros, they are economical. For example, as cheap as less than €5 per unit, and they have very low current consumption. But yeah, they have high noise, bias instability, and other temperature effects. And sometimes, like the recently manufactured MEMS sensors also have this automatic temperature correction, which is very good for the automotive industry, but not so good for the space industry. And this leads to incorrect attitude propagation in the eclipse phase. And also after every power cycle, for example, if the sensors need to be turned off for some reason, and whenever they are restarted, there's a something called turn-on bias, which means every time the sensor is turned on, the bias changes. And this needs to be fixed before the sensors are used for attitude propagation. Yeah, and for example, this can lead to a different range of errors. For example, on the satellites I'm involved in with at Technical University of Berlin, the error can go as high as 160 degrees in the eclipse phase after 35 minutes without recalibration. But on the other hand, with calibration, it can be as low as 20 degrees, but that's not a very good number. So there's definitely a need for better quality sensors. And here I'll give you an example of how the temperature effects look like. So these are data from the MEMS gyro on our satellites. This was before they were deployed in orbit. So these are 3 different gyros, and the 3 plots correspond to 3 different sensors, and these sensors were placed in a thermal chamber to test the temperature effects. And the sensors were at a fixed location, so the actual angular rate should be 0 degrees per second. But you see, due to the changing temperature, how the bias changes over time. And this bias, it depends not only on the temperature, but also on the rate of change of temperature. And it is not linear, and it is different for all 3 axes. For example, for this last sensor here, you can see on the x-axis, there is a change at a linear rate, but all of a sudden at 10 degrees, the rate of change changes, and this is something caused by this automatic temperature correction, which is a new feature in many MEMS gyro these days. And here you see the same information about the same sensor in orbit. So for example, before calibration, the error in the angular rate using MEMS gyros was something like this. Yeah, so there is 0.15 degrees per second in the y-axis, but after they were calibrated, it improved slightly. And by the way, this calibration happened. We did this calibration in the sun phase because that was the only place where we had some reference, right? So we used the sun sensors and the magnetic field sensors to calculate the actual angular rate, and then we compared it with the rate given by the gyros, and then we calibrated. We calculated some calibration parameters for the gyros, and we hope that these calibration parameters will stay valid for the next few orbits, yeah, or days if we are lucky. Yeah, but unfortunately, it did not give very positive results. Because when we use the calibrated parameters, the error for the first 10 minutes, 12 minutes, it stayed low, less than 4 degrees. But after 12 minutes, the error started increasing again. And we suspect this happened due to this automatic temperature correction, which is about which the manufacturers are not so eager to talk much. Yeah, we tried contacting the manufacturer to find out if there is a way to turn this off, but we did not have much success there. So these are the problems we face with the current MEMS gyros on nanosatellites. Yeah, and of course the solution would be to have something more robust and more accurate, like fiber optic gyroscopes. For example, there are companies like Exail and GuideMap and GrandStyle which develop space qualified fiber optic gyros, and these have been flown in missions in the low Earth orbit or geostationary orbit or even Lagrange points. But they are big, they are heavy, so 350 grams, and they consume power, which is not preferable for small satellites, especially nanosatellites. So For nanosatellite missions, the requirement is to have sensors which are small, economical, which have a moderate to high performance, and they are robust against harsh space environment. And they should be resistant to temperature variations, and also the turn-on bias should be manageable. And this can be potentially solved by the integrated optical gyroscopes, which we hope to come out of the INPHOMIR project. And then the output can be fused with sun sensors and magnetometers for attitude determination in the sun phase, and also propagation in the eclipse phase. This was about the integrated optical gyroscopes. Now I will talk about the second type of sensors, the LiDAR sensors, the frequency modulated continuous wave LiDAR sensor. And these can be used for small satellite proximity operations, for example, for sustainable space usage or for removing space debris. Yeah, so there are different sub-applications in this field. For example, one could be where two satellites are close to each other, and then the chaser, or which is the satellite over which we have control, it does some close proximity inspection at a distance of 10 to 50 meters, and then there can be rendezvous and docking where the two satellites actually dock to each other at a predefined velocity. Then there's something called berthing, where the chaser uses a robotic arm to attach itself to the other satellite. Can be used for in-orbit servicing, can be used for lowering the orbit of the other satellite so that it can re-enter Earth faster. Or this can also be used to raise the orbit of the target satellite so that it can stay for a few years more in orbit. Yeah, and another application could be to carry cargo to space stations, for which it will need to dock with the space station. All of these are considered to be done using nanosatellites here. So there are lots of sensors in this field, because rendezvous and docking has been going on for a long time now. So there are absolute sensors, which are the radar sensors, optical telescopes, and GNSS, which are useful for absolute navigation. But we are interested in relative navigation, which is finding out the position and velocity of one satellite with respect to the other. And for this, the sensors can be classified into far range and close range. One simple definition could be whenever the distance is more than 1 kilometer, it can be classified as far range. And for this, the typical sensors are radar or infrared or cameras. And then for the close range sensors, LiDAR can be used. Monocular cameras are very popular for close range, and something known as photonic mixture device, which are useful at very low distances. On the right, you see an image. This is from more than 20 years ago, but this is still valid. So this shows which sensors can be used at different relative distances. One rule of thumb is to have sensors where the accuracy is 1%, at least 1% of the, or below 1% of the range. So if we are at a distance of 100 meters, the accuracy of the sensor used should be at least 1 meter. Yeah, and of course for nanosatellites especially, and even small satellites, it's important that these key parameters are respected: the mass, volume, power. By illumination, I mean whether the satellites are in sun phase or eclipse phase. Its accuracy, of course, the costs, and the angular rate of the target satellite. If, for example, the other satellite is non-cooperative, which means if it's a space debris with no control, it might be spinning at some rate. So the sensor on the chaser must be should be able to estimate its angular rate. Yeah, and of course the operational simplicity. So the requirements for this sensor would be it should be able to calculate the relative position and as well as velocity at close proximity. It should be able to consider various illumination conditions because many sensors require the illumination by the sun for them to work correctly. And the sensor should also be able to detect the spin rate of the uncooperative target. And these are not suitable now with the traditional time of flight sensors. And this is where the frequency modulated carrier continuous wave LiDAR could be useful, because these sensors can calculate precise distance and velocity with a very high accuracy, and they have a better resolution than other sensors, and they can work in both sun and eclipse phase. They can also detect the orientation change to some extent, and this is useful for a spinning satellite or a tumbling debris for inspection, as I said. On the negative side, these have a higher complexity than time of flight LiDAR sensors. We can hope that the outcome of the INPHOMIR project can reduce the complexity which is expected from this FMCW LiDAR sensor, so that they can be used on small satellites. Here I present an overview of the commonly used sensors for close proximity. Yeah, so for larger distances, it's usually the radar sensor. But we plan to use the LiDAR, the FMCW LiDAR sensor at a very low distance. And all these rows they appear very good. The resolution is high, spin rate handling is excellent, illumination robustness is good, velocity measurement is possible, but of course the size, weight, and power complexity is higher compared to other sensors. Normally in such missions, there is no one sensor which works. It's usually a combination of different kinds of sensors. Yeah, so for close range distances, it could be an FMCW LiDAR working together with a monocular camera, and these are then used together in a sensor fusion outcome to calculate the final position and velocity. Here is another diagram to show when to use which sensors. So for example, if the distance to target is, let's say, within 100 meters, and if the spin rate of the target is very high, so if the target is spinning, then FMCW LiDAR is an obvious choice for the reasons stated before. Yeah, but on the other hand, if the spin rate of the target is expected to be low, or if the target is a cooperative target, which means that that the mission operators are still able to contact the target satellite, then perhaps it's not necessary to use an FMCW LiDAR, but go with a less complex camera system. For example, a time of flight camera along with a monocular camera, for example. And of course, for higher distances, greater than 100 meters, for example, radar can be an option along with a monocular camera. One important aspect of these sensors is their calibration. So of course, while using an FMCW LiDAR, it's important to test it on the ground with a dummy target model. So if we already know what kind of target satellite we will have in orbit, its dummy can be constructed in the lab on the ground, and then the accuracy of the LiDAR, of the FMCW LiDAR, can be tested on the ground itself under different illumination conditions or other factors. Yeah, and then once the chaser satellite is deployed, the one which is just carrying the FMCW LiDAR, in-orbit recalibration should happen, because there might be thermal mechanical radiation effects on the sensor. And also many sensors have internal calibration methods available using built-in reference paths. They should be used. And finally, the accuracy of the sensor should be compared with other sensors. For example, if the target satellite also has GNSS, the accuracy of the FMCW LiDAR sensor should be cross-checked with other sensors. Of course, this only works if the target is cooperative. Yeah, and here I want to show an example from. I want to show an example here. This is an image taken by the star tracker of one of our nano-FF satellites from Technical University of Berlin. So here, one chaser satellite, it's called nano-FF-B, has taken an image of, or has taken a series of images of nano-FF-A using its star trackers. This was 2 months ago at 1.6 kilometers relative distance. Yeah, so here, this green dot here, it's the other satellite. Yeah, and the blue dots here, play this again. The blue dots here, you see these are the stars, and the red dots here are the hot pixels. So my reason for showing this is that the outcome of the calibration process should be able to filter out such effects, such environmental effects, and should be able to calculate the distance from the data it has. I mean, here, of course, we knew already that this distance is 1.6 kilometers, but in the end, this distance should be matched. The known distance should be matched with the data seen from the sensor, and that's one of the ways of calibrating the sensors. Yeah, to summarize, there is a lot of potential for capable attitude estimation and relative navigation on small satellites. We need higher accuracy sensors, more robust sensors, and sensors which require less power, mass, size, and cheaper. And the accuracy of these sensors should be valid across all locations of the orbit, so both sun and eclipse phase. And their calibration should be possible in orbit for the best results. Yeah, with this, I end my presentation. If you have questions, I'll be happy to answer later.
Thank you. So, thank you, Dabdeep, and thank you once again to all our speakers for their clear and inspiring presentations, and to all of you for attending. Now, if you have any questions, feel free to raise your hand and I will activate your microphone. In the meantime, I will read a question during the Matteo presentation, which is it possible to try some of these photonics gyroscopes? What is the state of production prototyping? I don't know, maybe it's for Leonardo.
Yeah. Well, this is a question for us. Well, this project lasts till 2027. We expect at the end to reach the TRL 4.5 of this technology. We hope to make it faster, to provide some first, I mean, at least internally tested units by the end of 2026. But well, it's a it's still a low TRL project, and we are working on it. It will take some time still to be available for commercial for commercial application, and to be sold outside or after. For sure, the first users will be Sigma Engineeria and Endurosat for the testing, but I think that we'll need to wait the end of the project for this. We'll do the industrialization of this, and after this there will be a phase at TRL level in which some users like MDM, that is the one Vincenzo is the one that is generated this question, could be a potential user of this technology.
Yeah, thanks for the reply. First of all, of course, it's been a very interesting and detailed workshop, very well explained, very key concept set on a very professional way. Now, my question was, yes, for Leonardo, it was when we could put our hands on top of this photonics gyroscope, because I can see a lot of potential. And I have actually a question for the latest speaker, the one for the nano satellites. I was curious, when the satellite goes into the black orbit or the dark region, let's say, okay, I'm going to use the Star Wars
eclipse zone.
The Star Wars nomenclature. Can you actually use some aiding at all? So the only aiding you rely is the sun sensor, or I understood there is also some sort of magnetic aiding. Can that work also in the dark orbit?
Yeah, so usually we use sun sensors and magnetic field sensors for calculating the orientation in the sun phase. But then in the shadow phase there is no sun, so the sun sensors don't work. Yeah, and then so then we need to combine the magnetic field information and the angular rate coming out from the angular rate gyros. Yeah, but as I said, the issue is with the accuracy of those angular rate values itself.
Yeah. Okay, thanks. It was just curiosity, but great workshop, guys, and also of course to Matteo Bacini, which is the only one that I missed. Ciao, Matteo.
Ciao.
Okay.
I see a question from Saulan. What is the Q factor of this mirroring resonator, and do these photonic gyroscopes reach tactical range sensitivity? Well, about the Q factor, I'm not the main expert of the photonic chip. What is the level of Q factor that is needed to reach a given accuracy? But for sure, we expect to have a sensitivity that we expect to be in the middle of range between MEMS sensors and fog sensors. We expect to have better sensors than MEMS. And okay, a colleague of mine helped me in reply, because we expect 10 to 6 to 10 to 8 Q factor, and yeah, that would be 0.1 to 1 degree per hour accuracy. And well, it's in the middle between. It's much better than MEMS sensor, but still it doesn't reach the accuracy of the fog. But we expect in the future to make better. To improve this technology.
Okay, thank you. So if there are no other questions, we kindly ask you to take a moment to complete a brief feedback survey with your input, because it's very valuable to help us to improve future outreach and training activities with the INPHOMIR. So I'm gonna share you a QR code that link to the survey.
Okay, I have a question for Deep.
Yeah.
Well,
Yes.
can you tell me the discussion of temperature between the eclipse phase and the sun phase for a satellite? I mean, to understand which is the stress that you have for sensors, initial sensors.
Yeah, so the actual temperature, it depends on various factors, depending on where the sensor is located and how packed the satellites are. But for the NanoFF mission, for which I gave the example, it varies between 0 degrees and 20 degrees. Yeah,
Okay.
so in the eclipse phase, the temperature can go as low as 0 degree, and it can be as high as 20 to 25 degrees.
And is it fast, this transition?
It depends on what you mean by fast.
It takes minutes.
No, it is. So one orbit is about 97 minutes.
Mm-hmm.
And in that about 34 minutes is in eclipse. The transition, how much time it takes from low to high, it can take 30-40 minutes.
Okay.
To go from the lowest to the highest value. Yeah.
And is this transition modeled in some way? I mean, it's considered like because I mean more accurate is the modeling in the Kalman filters. More accurate, maybe it could be the forecast of what could be the behavior of the inertial sensor. Is it possible, in your opinion, to model this behavior?
You mean the behavior of how fast the temperature changes?
Yeah. No. How it could affect this change on the navigation. I mean, the fact that you can maybe forecast in some way this, because you typically don't have a really fast. Okay, maybe MEMS, you have a temperature sensor, and you may estimate which could be the drift of the output.
Yeah, I mean, what can be done potentially is to also consider how fast the temperature changes and have it as a parameter in the software. Mm-hmm. Because how fast the temperature changes for a satellite, no one really knows until the satellite is in orbit.
Okay.
Because it is very satellite specific, let's say, and also maybe sensor specific. So so this can be considered a parameter and then be fed back into the algorithm, which can compensate for this. But in our experience, the biggest problem for us was the automatic temperature correction, which was really
I can understand.
Not very helpful. And because we don't really know how it works internally, we can only see its behavior from outside. But we are sure that it depends not only on the temperature, but also on how fast the temperature changes. Mm-hmm. But then each sensor thinks in a different way. It has its own idea of how the temperature is changing. For example, because we also saw many random changes.
Yeah, I can understand. We had the same experience in the MEMS sensors that are affected the automatic compensation, and it's difficult to forecast what it's doing after some temperature, because I mean there is a compensation that is computed that sometimes can be very different with respect to what you expect.
Yeah.
But there is a question from Paolo Gelfi. Yeah, are you going to use standard indium phosphide, or will it be some heterotime platform? The reason for this question is that indium phosphide is not very transparent, so one could expect Q factor lower than 10 to 6, unless you do something fancy. The technology behind the the indium phosphide is mainly I would say managed by the Technical University of Eindhoven. And they for sure, they invested a lot on this technology, and they are doing a very good job on the to allow the ring resonator to have a high Q factors, and we expect values higher than 10 to 6. What they do so fancy is something that for sure they know, but it's not something that is spread inside the INPHOMIR project. Any other question?
I don't see any other question, but if you can please scan the QR code now visible on the screen, you can find a short survey for us. And I will reach you to sending an email to our participants with the link to the video registration of this webinar, so you can watch it again if you wish. And if there are no other questions, thank you all for joining us, and we look forward to seeing you again on next events.
Thank you all.
Thank you very much. Bye-bye.
Bye-bye.
Thank you very much. Bye-bye.
Bye.